This is a derivation of the Larmor formula. It can be found online in a variety of places. I think Berkefee and Barrett is a book that actually has the full derivation. Walter Lewin's 803 video class has also, part of it has that derivation. And Dr. Gauss' video series also, his electromagnetic series also has this derivation. So where we're going to start with is a charged particle located at the origin, and we're going to go ahead and start it here, and then we're going to accelerate it up to a particular point after delta t, and then we're going to let it coast for an arbitrary time. So we have point O, where the particle starts. We start accelerating it. Point O prime, where we stop accelerating it. And point O double prime, which is where the particle is actually coasting. So let's go ahead and write that down. So we have here, this is delta t, and acceleration a, and from here to here, we have a displacement ut, which is time t, and the constant velocity u. Notice that we say constant velocity even though we're accelerating it for that delta t interval. So what we're going to note here is that delta t is much smaller than t. Now, we're going to go ahead and draw a radius vector. It's arbitrary in which direction from here, but we'll go ahead and pick this one. And that's going to be radius r, and we're going to have the electric field in that direction. Right? Now, whenever we have an electric field, we have equipotential lines. So what we're going to do is we're going to go ahead and draw equipotential lines around point O, which is where we stop the acceleration. And of course it's a sphere, but in this plot we're going ahead and projecting it onto a circle. And we're going to do another similar equipotential line for the position O. So at O we have equipotential lines also, and they're going to go like so. Of course they're going to be further out because at O the electric field started propagating out, and then at O prime they propagated out, so they're going to be younger at O prime than at O. So to highlight that fact one more time, we have the O prime circle, which is this one, and in here we have r equals c, velocity of light, times t, and then the O circle here, where we have r is equal to c times t plus delta t. So again, the delta t interval is showing up here in our ripples of electromagnetic field. At O double prime, we're now going to note that we also have a field coming out. So we're going to go ahead and say that that field is propagating out up until that point. Now, the interesting thing is that the field, of course, at the end of the day is going to be, from this particle, it's going to be going out, and then it's going to be resuming here on the other side of this wake, or this lurch forward of our particle, which translates into a discontinuity of our electric field. Of course, electric fields have to be continuous, so we're going to go ahead and join these two lines and make sure, be careful about highlighting that this end is going to be a small curve as opposed to a sharp edge, as an electric field should be. The next thing we're going to do is we're going to draw a triangle that's perpendicular to our radius, and that one, I'm going to do it in blue, is going to be here, and on this side over here completes our right angle triangle. So this length here is going to be u perpendicular times t. Why? Because u is a vector, and we can decompose it into a perpendicular and a parallel components. So that's u perpendicular times t. Okay. So here we're going to have c times delta t, that interval there. Now we can go ahead and concentrate on the electric field in the zone of interest, which is during the wake itself. And here what we can say is the electric field is going to go, say, something like this. And we're going to decompose that electric field into a parallel component of the electric field and an orthogonal, or in this case, perpendicular component to the electric field. Now, this triangle that we drew outside is going to be similar to this triangle in here. Just we note that in passing. Looking a little bit at the velocities, we have a velocity u equals to the acceleration a over a time delta t. That's the acceleration that we imparted on the particle from O to O prime. And since we can decompose it into perpendiculars and parallels, we'll look at the u perpendicular and call that one a perpendicular times delta t. Now then, back to our triangles. Since they're similar triangles, we can go ahead and say that E perpendicular over E parallel is going to equal to U perpendicular times T divided by C times delta T. It should be noted the speeds that we're dealing with. Remember, R equals to CT, which is much, much greater than UT. So the velocity of light is a different realm than what we're just, the speeds that we're dealing with here. So back to our expression here, we feed that equation into this one, and we end up with A perpendicular times delta T times T divided by C times delta T. The delta T's cancel, and we end up with A perpendicular times T divided by C. And if we want to solve for E perpendicular, we have A perpendicular times T, in which, as a matter of fact, instead of T, we can actually call it R over C. And the C's multiply here, so we end up with C squared times E parallel. So the problem now becomes to learn more about E perpendicular, which from this graph it should be obvious that that's the one responsible for the electromagnetic waves. We have a radial component of the electric field, sure enough, but this perpendicular component is the one that's actually going to be generating that electromagnetic field, electromagnetic wave, that radiation. So let's find what E parallel is. For that, what we have to do is we have to go to Gauss's law, and again we draw part of our plot above, not the entire thing, but part of it. That's A there, and then our R, which is here. And just to note, what we're going to be looking at is this zone of interest around the outer shell. So for that, what we're going to do is, just like in Gauss's law in the past, we draw a pillbox here, and then we look at the fields coming in and going out of that pillbox. Easy. On the outside of the pillbox, which is at this interface right here, we have vector E. On the other side, which is the zone of transition, we have E parallel, which notice what we're looking for here. And then tangentially we have E perpendicular, E perpendicular. Per Gauss's law, the divergence of vector E over a closed volume we have equal to the enclosed charge. Since this is a traveling wave, the enclosed charge is 0. This translates into the tangential component, which is E perpendicular equal to the E perpendicular leaving, so those go to 0, whatever comes in goes out. E parallel, however, equals to minus vector E. So that's the result that we were looking for. Because what we can say now is that E perpendicular is equal to A perpendicular times R over C squared times E parallel, which is a negative Q over 4 pi epsilon naught R squared. We can simplify R's, and we end up with an expression for E perpendicular, which is E perpendicular equals to minus A perpendicular Q over C squared 4 pi epsilon 0 R. Go ahead and put that one in a box. Great. In a nutshell, we can summarize a little bit here. We can see we have E, vector R, position R, and time, vector E, position RT, is given by that expression. Again, we're looking into the zone of interest, into that, the intermediate, in between shells area. And then also we have B, function of position and time again. And that one, we know, is E divided by C, without considering too much the directions of these things. That comes out to be minus A perpendicular Q over, the C now becomes C cubed times 4 pi epsilon 0 times R. Okay? Now, what we can do here is we can look at the Poynting vector. The Poynting vector then becomes, well, by definition, Poynting vector, function of position R and time t, is vector E cross vector B divided by mu 0. In this case, it becomes, multiplying these two out, negative times negative is a positive, A perpendicular squared times Q squared divided by C cubed times C squared, C to the 5th times 4 pi epsilon naught squared times R squared. And we have a mu naught down below. Okay. Before we get too far away, let's look over here at A and see what A perpendicular is all about. Again, this angle right here is going to be theta. So if we say this vector A can be decomposed into A perpendicular and A parallel, it should be obvious that A times the sine of theta gives us A perpendicular. So then actually here we could say A perpendicular is equal to A times the sine of theta. So we can express this in terms of theta. Now then, one other thing, we can go ahead and pull 1 epsilon naught out of here, multiply it times mu naught, and since C squared equals to 1 over epsilon naught mu naught, we could replace that with 1 over C squared. So then, therefore, our Poynting vector as a function of position vector R and T equals to A squared sine squared theta q squared divided by c to the fifth divided by c squared, because remember we pulled an epsilon naught out of here times that one, gives us the inverse of c squared. So that's c cubed times 4 pi r quantity squared and the lone epsilon naught that remains. Interesting to note that the Poynting vector tells us the propagation, the power propagation, and we notice that we have a sine squared theta, which means that along the line of propagation of this charged particle, that's sine of 0, so there's no component of power going in that direction. However, at 90 degrees, we have the maximum. Either side, we have a maximum. As a matter of fact, since this is spherical symmetry, we have essentially what becomes like a ring of power, and more generally becomes a donut, which the axial direction has 0 power, but all the power is radiated in terms of a torus. Now then, the question that can be asked here is, what is the power averaged over the entire sphere? And that gets us then, we can integrate actually, we can come up with P for power equals to the spatial average of the Poynting vector, which is equal to, okay, let's go ahead and say Q squared times A squared divided by C cubed times epsilon naught times 4 pi quantity squared times a double integral of sine squared theta over r squared times the volume element. The volume element for a spherical integration is r squared sine theta d theta d phi. We can go 0 to 2 pi on phi and 0 to pi in theta. Immediately we see that the r dependence goes away. So the power is going to be constant for increasing r. And what we end up having here is we can say that integral of, with respect to phi, becomes an integral over 0 to 2 pi of d phi, which is phi evaluated at 2 pi and 0, which gives us a factor of 2 pi, since the 0 doesn't contribute anything. So given that, we have q squared a squared over c cubed epsilon 0 4 pi quantity squared times 2 pi, which comes from the phi integration, times 0 to pi sine squared times sine theta gives us sine cubed theta d theta. These two terms can combine, and we end up with divided by 8 pi times epsilon 0 times c cubed times this integral 0 to pi of sine cubed theta d theta. Now, we want to go ahead and evaluate that integral. So what we say is we use u substitution. Let u equals to cosine of theta. That implies that du equals to minus sine of theta. And then what we can say is we evaluate that integral by saying sine cubed theta d theta equals to 1 minus cosine squared theta times this integral right here, or times the sine theta actually there's a d theta here. And that now, using our u substitution, can become, a negative sign comes in here, so we put the first term in the front, becomes u squared minus 1 du. That readily integrates into 1/3 u cubed minus u, which then becomes 1/3 cosine cubed theta minus cosine theta 0 to pi. Now we can go ahead and continue evaluating by saying that's 1/3 cosine cubed of pi minus cosine of pi minus 1/3 cosine cubed of 0 minus cosine of 0. And here we can come up with that term being minus 1, that term being minus 1, that term being 1, that term being 1. So that then comes out to be 1/3 negative plus 1 minus 1/3 plus 1, which is equal to minus 2/3 plus 2, which is equal to 6 divided by 3 minus 2/3, which is equal to 4/3. That's the result that we wanted. We can plug that back in to our equation for power and come up with this expression. And the 4/3 here. This goes to 1, this goes to 2, and our final expression for power is here. This now is Larmor's formula. And you notice that the power then does not depend on angle, it does not depend on radius. As you increase the radius, you're decreasing the electric field, so the power remains constant. That applies again for speeds that are not relativistic, but that is a very useful result, and we will pursue it in antenna theory in future videos. That's all.